Hi everyone, this video will be on the Schrödinger model. We'll be discussing what the Schrödinger model is, SPDF subshells, what orbitals are, and the SPDF notation for electron configurations. Here are our relevant syllabus dot points. So the Schrödinger model is the most modern model of the three which we've looked at so far, the Rutherford model, the Bohr model, and this one is the Schrödinger model. We also know it as the quantum mechanics model. Now the Schrödinger model is actually slightly different to the other models because what it does is it mathematically describes to us where an electron might be. So it's going to provide us the probability of finding an electron's position around the nucleus. And if we look at the diagram on the right hand side, what we can see is we can see the nucleus with the many different electrons or potential electron positions which surround the nucleus. So it's important for us, really, to understand that unlike the Rutherford and the Bohr model, the Schrödinger model does not demonstrate an atomic structure that kind of resembles a solar system. Now, according to the Schrödinger model, electron shells contain subshells within them, and we give them these names S, P, D, and F. The lowest energy subshell within the electron shell is the S subshell, the P subshell, the D subshell, and finally the highest energy is the F subshell. Now within these subshells are unique shapes or unique orbit pathways in the subshells which we call orbitals. So the S, P, D, and F subshells each have their own orbitals, and on the right hand side we have the orbitals which provide us with the shapes of the particular pathways which the electrons can have around the nucleus. So for example, this is the S orbital which exists in the S subshell. These are the P orbitals, these are the D orbitals, and these ones are the F orbitals. So the S subshell is the lowest energy level subshell, and that's where we would find our very first set of electrons. So orbitals are denoted with the letter, which is going to tell us which subshell it's in. In this case, we're in the S subshell. And it's going to give us the letter which is going to tell us what the energy level is. Now the first energy level is going to be energy level 1, so 1s is the lowest energy orbital in the S subshell. Now the S orbital is defined by its spherical appearance, and if we look on the right hand side we can see that it has this circular sphere appearance where we have this cross section cut out here for the 1s orbital. Another thing that's important for us to know is that within each orbital, it can hold a total of 2 electrons. So the highest energy orbitals of group 1 and group 2 and helium elements are going to lie in the S subshell. This will be important later when we learn about notation. So if you looked at the diagram on the right hand side, what you might have noticed is that there are these red shells and these white areas within them. And you can see that this is labeled a node. So what a node is it's an area that's defined by having 0 electron density. And what that means is these are areas which we cannot find any electrons in. Now the way the diagram works is we can see the 1s lobe over here. So lobe is going to be the area which does have electron density. And we have the 1s lobe here in red. So if it was in the 1s orbital, we would find electrons in any of these areas over here. Now with 2s, the 2s orbital is going to be the outer side, and the electrons are going to be found in anywhere here. And then the 3s orbital is going to be on the outside, and it has the node which separates the 3s from the 2s and the 1s energy level. So what is important about understanding nodes and the existence of lobes? Well, what it does is it demonstrates and it provides us evidence of the quantization of energy levels for each of the electron subshells. So the next subshell is the P subshell. Now the P subshell is defined by its dumbbell shape, which we can see over here, this sort of round 2 lobes on the 2 sides. So we can see that there are 3 p orbitals in the P subshell. So in the P subshell there's the p orbital that runs in the x-axis, there's p in the y-axis, and there's p in the z-axis. These are going to be the 3 dimensions and these are going to be the 3 planes in the 3 dimensions which we can see. Again, we can see just like with the s orbitals, there are these nodes which are visible between each of the lobes on the 2 sides. Previously we said that a total of 2 electrons can exist in each orbital. Now in the p subshell, at each level is going to have 3 orbitals, which means that we can have 2 orbitals in each to give us a total of 6 electrons. Now elements in group 13 to 18 are called the p block elements because their highest energy electrons are going to lie in the p subshell orbitals. Now the next subshell is the d subshell. The d orbitals appear as this clover or double dumbbell shape, which we can see on the right hand side. This is all with the exception of the dz squared orbital, which has a slightly different shape with the ring lobe and the 2 lobes on the side. Now what's important? Now the d orbital has 5 orbitals, and if we remember again, each orbital contains 2 electrons, which means that there are a total of 10 electrons which can exist in the d orbitals of the d subshell. Transition metals are going to be the elements which have the highest energy electrons in the d subshell. That's groups 3 to 12. The final subshell is the F subshell. The F subshell has the highest energy, and it has an appearance which is difficult for us to describe, so we just say it has a tetrahedral alignment. Again, this time the Fz cubed orbital is going to look very slightly different to the other ones which we can see over here. Now the F subshell is going to contain 7 orbitals per subshell, and if we have 2 orbitals in each, we can have a total of 14 electrons. Now the lanthanoids and the actinoids are going to be the elements which have the highest energy electrons in the F subshell orbitals. So SPDF configuration notation is a unique configuration which we use for each of the elements. It denotes which electrons in the element are in which of the sp, d or f orbitals and levels, and is helpful in determining the elements. Here on the right hand side we have a periodic table which demonstrates the different block elements with the s block in blue, the p block in pink, the d block in orange, and the f block in green. So what this means is that all of these s block elements have the highest energy electrons in the s orbital, then the p block elements have them in the p orbital, d in the d orbital, and f in the f orbital. Another reason why SPDF configuration can help us identify and determine elements is because the number of energy levels is equal to the number of respective orbitals. So for example, in the energy level 1, there is only one orbital which exists, and that is the 1s orbital. In n equals 2, there is a 2s orbital and a 2p orbital. Then in the third energy level, there is a 3s orbital, the 3p orbitals, and the 3d orbitals. And then in n equals 4, there is 4s, 4p, 4d, and 4f. So these configurations, or these specific placements of electrons in the particular orbitals, is going to help us determine what the element it is that we're looking at. So we'll have a look at the periodic table diagram again. Now the obscure shape of the arrangement of the blocks of the periodic table can be explained by the order of energy level filling which is necessary. So let's just look at hydrogen and helium. So hydrogen's here and helium is here as our first examples. So each orbital can only contain a maximum of 2 electrons in each because they're in 1s. Now hydrogen has 1 electron because it is the first element on the periodic table, and helium has 2 electrons. For hydrogen, the electron is going to be assigned the very first available orbital, which is the 1s orbital. So 1 electron will go into the 1s orbital. For helium, there are 2 electrons. Now remember that each orbital can hold a maximum of 2 electrons, and so both electrons will go into the 1s orbital. However, if we move on to element number 3, lithium. Lithium has 3 electrons. We can only fill a maximum of 2 electrons in the 1s orbital, so there is going to be 1 remaining electron. This electron is then going to be assigned to the next electron orbital, which is going to be the 2s orbital. This 2s orbital can hold a maximum of 2, and with 1 electron being filled up from lithium, it now has 1 vacancy. And so this lithium would have an electron configuration of 1s2, indicating the number of electrons, and then 2s1. We'll go into more detail about this when we do some examples involving SPDF notation. So when we write SPDF notation, there are three major rules which we must follow, which is called the Aufbau principle, Hund's rule, and the Pauli exclusion principle. So the first rule is called the Aufbau principle, which states that each electron occupies the lowest energy orbital available. If we look at the periodic table again, we can see that for element silicon, number 14, the highest energy orbital which is available is going to be the 3p orbital. Now if we look on the diagram on the left, what we realize is that if it has up to the 3p orbital as the highest energy orbital, then it's going to have 1s available, 2s and 2p available, and then also 3s and the 3p available. Now the order of filling the electron orbitals is going to follow this kind of direction like this over here. So if we take this into consideration, what the Aufbau principle is really saying in essence is that we have to assign electrons into their respective orbitals in the correct arrangement or order. This means that we cannot have the first two electrons in the p orbital, then fill up the s orbital, then fill up the p orbital. It must follow this particular direction. The next two rules are Hund's rule and the Pauli exclusion principle, which we will treat together. Hund's rule states that electrons must occupy equal energy orbitals before opposite spin electrons can occupy them as well. The Pauli exclusion principle states that a maximum of 2 electrons with opposite spin may occupy an orbital at any time. Now for the purposes of Year 11 HSC chemistry, we do not need to delve into what spin is, just know that it is a quantum property which electrons have. So in essence, what really the Pauli exclusion principle is saying is that there can be a maximum of 2 electrons in each orbital, which we talked about before. So now we'll do some examples of SPDF configuration diagrams to help demonstrate the three rules in combination. As discussed earlier, we use SPDF notations to identify elements, and we can also similarly use the configuration diagram in order to do so as well. Here we have 3 elements, hydrogen, lithium, and oxygen, to help us aid our understanding. Now in the case of hydrogen, it has only 1 electron, which will go in the 1s orbital because it is the lowest energy orbital that is available. We write out 1s, and we know that the s subshell only has 1 orbital, so we draw one line to demonstrate the orbital. For lithium, there are 3 electrons, so 2 are going to be going into the 1s orbital, and then after that is going to be the 2s orbital, because if we remember, we can only have a maximum of 2 electrons in each orbital, so if there's 2 here, then there must be 1 left over here. Oxygen has 8 electrons, which means that there are going to be 2 in the 1s orbital, there are going to be 2 in the 2s orbital, and then after the 2s orbital is the 2p orbital. Now the 2p orbital can hold a total of 6 electrons, because if we remember, there are 3 orbitals in the p subshells, so 2p will have 3 orbitals, which are demonstrated by these lines here. Here is just a neat version for us to confirm what we have done so far. After that, we can start filling up the orbitals. So in order to indicate the 2 opposite spins, we give it a single headed arrow, like so. So there's 1 electron in 1s for hydrogen, and so we have this one line to demonstrate that 1 electron. Now I'll show you what it means to have the opposite spins as shown in Hund's rule and in the Pauli exclusion principle. So lithium has 3 electrons. 2 will go into the 1s orbital, so we demonstrate the 2 opposite spins by giving them these single-headed arrows in the 2 different directions like so. And then we're going to fill up the last one, because there are 3 electrons in the 2s like so. It can be either up or down. Now for oxygen, there are 8 electrons, so let's just fill up the 1s first. We have 2 in 1s, we have 2 in 2s, and we have 4 in 2p. Now what you might be tempted to do is to draw them like so, like this, like fill them up like so, but this is not correct. What you actually need to do is you need to add them one by one. So this is where Hund's rule comes into play. It says that single electrons must occupy each orbital of the same energy level first. So what actually needs to happen is this. We need to fill up the last four like so. 1, 2, 3. Because each of the equal energy orbitals have been filled with one spin, electron, we can then continue to fill up the rest of it. We have one electron left and that goes into the first one and it looks like this. This is what our electron diagrams are going to look like for the SPDF configurations. We can also express SPDF configurations with notations. SPDF notations follow the same order of orbitals, starting with 1s, 2s, 2p, etc. In the case of the SPDF notation, instead of drawing arrows next to the written orbital levels, we simply write numbers indicating the number of electrons which exist in that orbital. So for example, with hydrogen, which has only one electron, we only have the one electron in the 1s orbital. So we will write this as 1s and 1. So the superscript is going to indicate the number of electrons in that orbital. For lithium, it will be 1s2 and then 2s1. Sodium has 11 electrons. So there are going to be 2 in the 1s orbital. There are going to be 2 in the 2s orbital. There are going to be 6 in the 2p orbital. And then finally, after the 2p orbital, we hit in the 3s orbital. And there's going to be just the 1 remaining. So this will be 3s1. Phosphorus has 15 electrons. So there will be 1s2, 2s2, 2p6, 3s2, and after 3s2, we've now used up a total of 12 electrons. There are 3 remaining electrons, and they will go into 3p. So that will be 3p3. Here we can check our answers. So now we can briefly go back to this periodic table again to look at why we do not need to memorize the order of the SPDF notations. We can work it out by recognizing the blocks of the periodic table. Group 1, 2, plus helium are going to be in the S block. So these are going to go 1s1, 1s2. Then to the second energy level will be 2s and then 2s. And then it will be p, and then it will be s, and then it will be p, s, d, and then p, following this particular order. Now for the purposes of HSC chemistry, they will not be asking you to write the notations for F block elements. In the Bohr model video, we briefly talked about the octet rule as being the rule which states that electrons aim to have 8 valence electrons or a full valence shell in order to become stable. Now in actuality, this is not so unlike with SPDF notation, where atoms aim to have a full s and p subshell orbitals. This s2p6 notation is also known as the noble gas configuration, because if we look at the noble gases neon and argon, we'll notice that they end their final 8 electrons with the s and p orbitals. Transition metals, as we discussed earlier, are part of the d block elements. The d orbitals are filled after the s orbitals. So when we write out the notation for transition metals, we'll typically have it written like it is with the transition metal iron, where it becomes 3p, 4s, and then into the d block 3d6. So you may be wondering why it is that we fill up the 4s orbital before the d orbital. The reason for this is because of the Aufbau principle, which states that the 4s orbital positions are going to become filled first because they are lower in energy. Chromium and copper, however, have exceptions. For chromium and copper, an electron in 4s is promoted to 3d5 and 3d10 instead. Now, according to the Aufbau principle, we should have 4s being filled before 3d, as we just talked about. However, in these circumstances, at one particular point, the 3d orbital is momentarily going to be lower in energy than the 4s orbital, which is why the electron makes the transition from 4s to 3d. So unlike the expected notation which we get, where we are going to be ending on 4s2 and 3d4, what we actually end up getting for chromium is we get 4s1 and then 3d5. Similarly for copper, we expect this 3d9 4s2 notation, but what we actually get is we get 3d10 and 4s1. Now this is a disruption in the rules which we'll have to know as exceptions for chromium and copper, but the other transition metals configurations are unaffected by this rule.